Good morning, everybody. Anybody happen to be in a supermarket or liquor store, see a bottle of hard liquor, like good stuff like vodka, and think of ethanol, that's an alcohol? Or do you happen to look at a bottle of rubbing alcohol, if you happen to be in a supermarket, and think, ooh, look at the label and it says 2-propanol, more like it'll say isopropyl alcohol, which is an alcohol? Or did you happen to look in the same supermarket or from your home, a bottle of nail polish remover? See, it says acetone, which is a ketone. Did you do that? It's a tough group. I will not give up when you walk out that door. Think about organic chemistry once in a while. It will not hurt. Trust me, I guarantee it. It shouldn't hurt. All right. Quick two announcements from the management meet. One is a week from today will be test number 2. I've already gone through the material that will be on test number 2. You should have gotten an email, and there's an announcement on Blackboard. And I will start promptly at the top of the hour. Also, those who have lab today, remember, I will enforce, if you're more than a couple minutes late, you will not be allowed to do the lab. Also, you need to leave there and launch the top or lab coat. You can see I have one of my acid shirts on. I wear one's clothes, and hopefully you will too. And I guess one other thing, coming events, next Monday, I will be going through the aldehydes and ketones problem set. I'd highly recommend you try it before I go through it. And then I believe I asked and everybody said yeah. So back by popular demand, this Tuesday will be the review for the next test. In this case, test 2. All right, let's go on to new material. This will not be on test number 2, but it will be on test number 3. And that is carboxylic acids and their derivatives. Ooh, new word for you to learn. Derivative. That means a substance or chemical made from something else, derived from, made from. In this case, it's a derivative of carboxylic acids, and carboxylic acids are used to make many things that you use in daily life. Sort of a little teaser, what will be coming up this chapter? Well, I'll talk about stuff that smells really good. I'll talk about stuff that really is sour to the taste, really sour. And then a couple exciting things. I'll share with you our family's secret spaghetti sauce recipe, which relies on organic chemistry knowledge. And probably the best thing I'll talk about this chapter is the first reaction I ever ran with my hands. Because once you're born, you're running, actually before you're born, you're running reactions in your stomach and elsewhere in your body. But this is the first chemical reaction, actually it was an organic chemical reaction I ever did with my hands. All right, let's talk about carboxylic acid. It's a new functional group. It contains a carbonyl, and let me not forget this. Carbonyl, carbon double bond to oxygen, and it also has a hydroxyl group, and it has carbons. And this is a carboxylic acid. Carbonyl, hydroxyl group, R group. And there are different ways to write this. Get to the next slide, you'll see. And my software doesn't always like to put the carbon here for the test. I make sure I override it. There are different ways of writing it. This shows the bond angle of the carbon there. Remember, like in a ring, I don't do it in my lectures for acyclic compounds, but every bend in a line is a carbon. So carbonyl, more likely in lecture, I'll draw it like this, or you'll see me draw it like this. Another way you can draw it, or write it, is like this. And another way is like this. On a test, I'll either use this or this or this. The other ways you'll see in the internet and other places, it's shorthand. On a rare occasion, I'll write it that way, but usually I don't. I think this, and this are just cooler ways of showing it. and then all carboxylic acids. So how do you name a carboxylic acid using the IUPAC rules? Good question. Thank you. Well, let's get a carboxylic acid up on the board. And the first thing you should be doing always when looking at an organic molecule is say or answer the question, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Ooh, not one, but two oxygens. And they're bonded to the same carbon, carbonyl, carbon double bond to oxygen, hydroxyl group, carbon with a hydroxyl group, and carbons. And it's a carboxylic acid. How do you name a carboxylic acid? You find the longest chain that has the carbonyl carbon, carbon double bond to oxygen. Well, 1, 2, 3, 4, 5. And since you all learned the table with the alkane names, 1 through 10, 5 is pentane. Now, because it's a carboxylic acid, you drop the E at the end of the A and E of pentane, which I already did, and you replace it with the letters OIC and the word acid. So you now have pentanoic acid. Now, just like aldehydes, the carbonyl carbon in a carboxylic acid is always number 1. Therefore, since everybody knows this is number 1, we don't put a number. And if you do, I'll take off points on the test because it's wrong. You don't need a number. So I'm done. Pentanoic acid. That was fun. I'll have you do one. Now, the nice thing is, all the rules you learned for substituents, alkyl groups, are still the same. And I'll ask you, what is the IUPAC name for the following molecule? I think you have the knowledge to go ahead and do that. And while you're doing that, I should warn you, this is another area I've worked extensively in industry, so I'm going to have a good time talking about it. And we'll come back to this when we talk about fats and oils, because that's really where I work with these carboxylic acids. Does that feel good? You can do this stuff? We'll be able to do it shortly. Yeah. All right, looks like everybody's done. Let's take a look at this molecule. Question is 3 points. Give the IUPAC name for the following. That's 1 and 2 important skills you should have in organic chemistry. Here's a molecule. How do you name it properly, meaning the IUPAC name? And we look at the molecule and say, what's different? And I look here, ooh, 2 oxygens. That's different. 1 is double bond to this carbon, carbonyl group. And that same carbon has a hydroxyl group, carboxylic acid. And now I know I have to find how many carbons is the longest chain. Don't know. That include the carbonyl carbon, carbon double bond to oxygen, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. And I hope you all agree, using your high-level math skills you need for my class, 7 is greater than 4. That's heptane. If it was an alkane, it's a carboxylic acid. You drop the E, add OIC, and the word acid. Am I done? No, because as soon as I say heptanoic acid, that's spoken for. What's left over? Well, I needed a pick-me-up this morning, so I put down my favorite alkyl group, T-butyl or tert-butyl. You can use either one. Most organic chemists, like myself, will say T-butyl because we're lazy. What carbon is it on? Carbonyl carbon is 1. This is on 2. So that's 2-T-butyl heptanoic acid. Oh, that was fun. Let's do another one.
I have a question.
Question? Yes.
So when you are numbering the carboxylic acids, you always start with that carbon attached to the
Carbonyl
oxygen?
carbon is always number 1.
Okay.
Always. I'll bet money on it. And as soon as I say that, you know I've already won.
Okay.
Because I won't say that unless I know I've already won. But, which I'm not teaching in this class, any molecule, even with other functional groups, the carbonyl carbon of a carboxylic acid will always be 1. What I don't teach in this class, because I just don't have the time, it would be fun to, is there are UPAC rules of when you have other functional groups, how to name them. Like if I also have a double bond in there, if I have an alcohol or ketone also on there. And in all cases, the carbonyl carbon will always be 1, which is why we don't have to put the number. Good question, thank you. Same question, what would be the IUPAC name for the following molecule? Have fun. And don't forget, I'm on YouTube. Nobody from Hollywood has contacted me to put a gold star on the sidewalk yet. Oh, that went over everybody's head. Or just dropped like a lead balloon. Yeah, it looks like everybody's done. I think the last letter just went down. We look at this and how do we name it? We identify the functional group, which is another way of saying look for what's different. 2 oxygens. This one is double bonded to a carbon and also has an oxygen with a hydrogen, same carbon, carbons here, carboxylic acid. How many carbons in the longest chain with the carbonyl carbon? Don't know. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5. So the longest chain, I hope you all agree, is 5, which is pentane. It's a carboxylic acid. Drop the E, add OIC, and the word acid, pentanoic acid. As soon as I say that, that's spoken for. Oh, look, it's your old friend, the methyl group. And they're not 1, but 2. So how do we say 2-dimethyl? What carbons are they on? Carbonyl carbon is always 1. You don't put the number there because everybody knows it's 1, 2, 3. And we have 2,3-dimethyl pentanoic acid. And that's how you do carboxylic acids. Now, there's one carboxylic acid that has been around and had a common name. I'll talk about some other common names, but I should do it now because the common name became the IUPAC name, and that's when R is a benzene ring. Carboxylic acid, carbonyl with a hydroxyl group, and we have a benzene ring. And IUPAC, in their infinite wisdom, and I truly mean this, they did an amazing job, and still to this day keep it amazing. And that is, instead of calling this benzeneoic acid, they call it the common name, benzoic acid. And you should know, if I ask, what's the IUPAC name? That's benzoic acid. If I say, well, I'll go through it in a little while, some other examples, draw the structure, that's and give you the name benzoic acid. Now, one of the things you should always be asking yourself, and I'll cover this in detail later today or next week, if I have time. Yeah, I'll have time, I'll get into it. A derivative, something made from benzoic acid, helps keep all your pop fresh before you consume it when you go to the supermarket. By the way, I'm from Chicagoland. Stuff in a bottle or a can that's carbonated, non-alcoholic, we call pop, not soda. But anyways, there's a derivative in there of this molecule, something made from that keeps the pop from going bad. So it's safe to drink and taste good. That's cool. All right. Now, there are two skills organic chemists should have in terms of nomenclature, how to name things. One is, here's a structure, give the IUPAC name. The other is, here's the name, draw the structure. And how do you decode the name to know what to draw? You start always at the right and go this direction. So if I start at the right, I say, ooh, acid, and the letters OIC. And as soon as I see that, I know I'm dealing with a carboxylic acid, carbonyl, carbonyl bond to oxygen with a hydroxyl group and an R. Well, if this were instead of OIC acid an E, that'd be octane, and I know that's 8 carbons. And you can write it on either end. I write it on the right always, that's how I learned it. In good habits, Dr. White doesn't change. And therefore, carboxylic acid, first carbon, I have my carboxylic acid group. Then I go this way and say, ooh, N-propyl, 3 carbons to the N carbon. Where is that? On carbon 3. I know this is carbon 1, 2, 3. 3 carbons. I haven't said this in a while, but you know there's 4 bonds to carbon, so I know how many hydrogens to put in. And also, let me remind you, it's your solemn responsibility that if I make a mistake, to correct me. Hopefully I won't, like I just did. And here we have 3 N-propyl octanoic 8 octanoic acid, carboxylic acid. And that's how you take the IUPAC name, or in a little while I'll teach you some common names, and draw the structure. And I'm going to share the fun, so what's the structure? Draw the structure for 2-ethyl hexanoic acid. We're having a lot of fun this morning. around the room. I gave myself a quiz, and I got 100%. I think I know everybody's name and face, so you're all no longer anonymous students. Look out. That's the thing. All right, looks like, wait. I'll give you 6.5 seconds more. 1, 2, 4. All right, so time's up. All right, let's take a look at this. And question is, how do you decode the name to determine what's the structure? Start at the right, move this way. Ooh. Oh, I see in the word acid, carboxylic acid. If this were an E, that's hexane. Hexane is 6 carbons. At one end, I'm going to do the right, you can do that end too. This is my carboxylic acid. This is 1, this is 2. On carbon 2 is like, oh, I have an ethyl group. That's an alkyl group with 2 carbons. And what carbon is it on? Carbon 2. Put in my hydrogens. And I'm done. And I've already spoken about some molecules, say hello to my old friend. This is a very evil, nasty molecule. I hate it because it caused me about 6 weeks of grief. Why? Because I was doing some, I developed a way to make a new compound, and I actually done all the lab work. We actually did it in the pilot plant. When you commercialize new chemicals, you don't just say, oh, let's make it in the plant and make 40,000 or 60,000 pounds. No, you start in the lab up to a pound, then you go what's called a pilot plant where you do up to about 500 pounds. When you scale up, you encounter things you didn't encounter at smaller scales. It would be the same thing if you're cooking breakfast, scrambled eggs. You do it for yourself, a couple eggs, that's one thing. Do it for 4 people, it's a little more challenging because now you're using more eggs, bigger frying pan. And now what if you're doing it for 2,000 to 5,000 people? It's a lot different. Well, same thing happens in the chemical industry. Well, we're ready to go to the plant, and the plant manager said in a meeting with me and some other people, engineers, yeah, I have some questions. Could you go back to the lab and just check this out? And I said, sure. And something I had already done a long number of times, all of a sudden, didn't work. What's going on? And I'm getting upset because it should work. And unfortunately, I forgot what was probably one of the best mentors in my life. Sid Shapiro always taught me and beat into my head, never assume because you become the first 3 letters. And finally, when I remembered that lesson, I looked at what was the starting material. It was from a reputable company, extremely reputable, and I just opened a new bottle, and I hadn't checked, is this stuff really pure? It's supposed to be 99.9% of the aldehyde, and it turned out there was about 40% of this in that bottle, which it shouldn't have been, that was causing all the problems. And once I figured that out, I knew, okay, it's time for me to solve it and get a fresh bottle and check it. And evil. All right. I gave you an evil one, I better give you a nicer one to try. Draw the structure of the following compound, and this doesn't look it, but you would write this. Now it looks better. 3,3-dimethyl nonanoic acid. Say that 5 times quickly. take a look at this. How do you decode this to know what to draw? You start at the right, O, acid, and the ending OIC. That tells me I have a carboxylic acid. If this were an E, that would be no name, which is 9 carbons. N carbon is a carboxylic acid. And then, ooh, methyl, I know that. Diamines 2, where are they? They're both on carbon 3. So 1, 2, this is 3. I have my dimethyl, and now I can put in my hydrogens. And that's how you do carboxylic acids. Carbonyl with a hydrox group to carbons. And as we'll see, they're in your everyday life. You even have one in your kitchen. No, I don't have carbons. Yes, you do. All right. Now, there are some key common names I would like you to know how to draw the structure. The first one is formic acid. Turns out, as simple as carboxylic acid, you could have the R group as a hydrogen. And nobody calls this, the IUPAC name would be methanoic acid, because it's this methane in one carbon, but everybody calls it formic acid. And it has all the properties of a carboxylic acid, including how the reactions it undergoes, and therefore it is a carboxylic acid. Now, one of the interesting things about this molecule is, how many of you have ever heard of the fire ants? Luckily, they're not in Illinois. Those are ants that have a defensive weapon that they spray something to whoever's attacking them, and it causes a burning sensation like you've been burned by a fire. And what the fire ant really sprays is a mixture of formic acid, a heated mixture of formic acid and water. And what happens is, whoever attacks an animal or person, or thinks the ant thinks it's going to be attacked as a defensive weapon, gets that on, and it burns like a burn, and that's why they're called fire ants. I've never seen one, I hope I never do, but they use formic acid. Now, the next chemical I'd like to talk about is acetic acid. And acetic acid is a carboxylic acid, carbonyl bonded with a hydroxy group to carbons. In this case, R is this one carbon, a methyl group. No one calls this ethanoic acid, otherwise to say you'd never call it ethanoic acid, which is the IUPAC name, 2 carbons, ethane, OIC, acid. No, everybody calls it acetic acid. And it's in your house. No, I don't have acetic acid. I would know if I have that in my house. Well, you do. And where do you find it? Well, if you take approximately 96% water and about 4% acetic acid, mix it together, you get a nice homogeneous clear solution, and you call that vinegar. And no matter what type of vinegar you have, whether it's plain old what they call white vinegar, or apple cider vinegar, or champagne vinegar, or some of the Japanese vinegars, which I like, and they're all essentially acetic acid and water. The ones that have the different tastes have some other minor constituents that you taste to give it, like apple cider vinegar, that special taste that's different than white vinegar. But essentially, they're all approximately 4% acetic acid, 96% water. So the next time you happen to be in your kitchen, pick up a bottle of this vinegar and say, aha, we don't have to say the aha, but you know, you can look at it and say, that contains this carboxylic acid. Now, it turns out it's not only the vinegar, but if you happen to open your refrigerator and pull out the ketchup or mustard or pickles or also relish, if you keep those condiments in your kitchen, in your refrigerator once it's open, you'll look on the label and they all say they contain vinegar, which means they get their taste, and I'll talk about in a little while, from acetic acid, part of their taste. So remember the first day I said, organic chemistry, my world of organic chemistry is your world, what's that? But you just don't know about it, now you're finding out about it. Yes, Bridget?
I was actually wondering, since you're mentioning vinegar, what about balsamic?
Yep. It's just got other things in there to give it its taste. If I'm correct in how they make balsamic vinegar, and don't quote me on this, because I've never made it myself, is they age it in a wooden barrel. And what that does is it takes some of the chemicals out of the wood to give it that taste and color. Now, other companies do the same thing with other types of chemicals, and they put water and ethanol in wooden barrels, and they make things like scotch or bourbon to give it that taste.
How about citric acid?
What? I'll get to that. It's a carboxylic acid too, but you're a couple of slides ahead of me. Could you wait? Thank you. All right. And the last one on there I've already talked about, benzoic acid. And it's a common name, but it's also the IUPAC name. And that's when R is a benzene group. So you should know on the test, I will never put a structure of either formic or acetic acid and say what's the common name. I could ask what's the IUPAC, but on a test, I could ask, draw the structure of either formic acid or acetic acid. I guess I could put on a test, name a use of acetic acid, a product with acetic acid you use in your daily life, and what could you use? Vinegar. All right, next slide. I'm turning the switch. We'll just be on test number 3 off, because we'll talk more about this in fats and oils for test number 4. So I'm turning the switch, clip off. We have longer chain fatty acids, or long chain carboxylic acids, and I'll teach you later. They're called fatty acids because they're derived from fats and oils, and that's where R is very long. Example, and don't write this down, we'll learn it later. This is called stearic acid, and I'll teach you ways where this is being used. These are all used in many things you use in your daily life, or compounds made from these carboxylic acids. Where we get into fats and oils, I'll teach you about how these derivatives of carboxylic acids are used in your skin creams, your hand lotions, a lot of other personal care things like shampoos, conditioners, and a lot of other things too. So these are very important. Again, switches off. See, I didn't lie to you, Alex. All right, how many of you ever worked out and all of a sudden your muscles, you feel this burn, it's burning, and they say, oh, if you watch one of Schwarzenegger's movies, no pain, no gain. But anyways, I'll let you figure out which movie that came from. But Running Man. But probably give it away. But you hear that, what's causing that burning sensation in your muscles? Well, it turns out it's this carboxylic acid, lactic acid, and don't ask me why your body makes that, because I'm an organic chemist. I don't know those things other than I know it does. And lactic acid is what's used your body, I guess, as a defensive mechanism. Technically, well, you better stop, something's wrong here. But that's lactic acid. Now, one nice thing about organic chemistry, I get to go into things you never thought I'd get to go into. And one of my, I wouldn't call it a hobby, but just curiosities. when I see a product, I wonder, how did they do that? And I think, wasn't there a show on cable, how did they make that or something like that? Yeah. How do they do that? And since I'm an organic chemist, and plus you're learning organic chemistry, how do you determine that? One way is just look at the ingredients labels. What chemicals are in there? That will usually give you the clue to how do they do stuff. Well, this is something I'm not in any way telling you go out and buy it and use it, or in any way moral significance to it, but it's real life. You can go and get this at Walmart and other Target and other places. I think you're all familiar with, or some of you are familiar with the product. That's a personal lubricant or gel, and it's used for certain activities. And a while back, a certain company called KY, and if you're familiar with their brands of products, came out with a warming gel that's used on certain personal parts to warm during certain activities. I wonder, how the heck did they do that? And the original formulation, I picked up the bottle, I'm looking at it and it says water and some other things. Now that one, all of a sudden I see lactic acid. All right, they're giving you a very slight acid burn that will warm you up. And that's how they did it. And I further, which I won't teach in this class, there's online, since 1995, probably the second best website I know on the internet. First best website or webpage is Google. But second one is the United States Patent and Trade Office, where they have all patents you can look at. And patents give you a wealth of information and knowledge. That's probably the most important website besides Google I go to. I spend at least 4 to 10 hours a week on that, doing work for myself. And I found the patent for this product from KY, and lo and behold, yep, it was lactic acid that's causing that. But I guess it caused some problems because they changed the formulation to something else, and now what causes that is a certain alcohol in the heat of hydration. When it encounters any moisture on the skin, it warms up because it's solvating the alcohol, and that's causing the heat. Now what I haven't figured out, I sort of know but I'm not positive, is they also have a product called fire and ice. I know how they do the fire, I don't know how they do the ice. Now, another thing, chemical, again, these I won't put on a test, but I thought you'd like to learn about it, is citric acid. Now, citric acid, my software didn't want to do it, I'll draw it, I might be more familiar with to you. As you know, I don't work with citric acid, so I don't remember the exact structure. And this is citric acid. And most of you have probably encountered it. It's an interesting molecule that probably the greatest of all organic chemists, Mother Nature, created. And this is the molecule in lemons and limes. If you ever drink lemonade or have something with limes in it, you know how it has that sour taste to it? This is the molecule that causes that. There's more citric acid in lemons and limes. That's why if you bite into a lemon, it's more sour than when you bite into or drink lime juice versus lemon juice. It's just the amount of citric acid. And this is a solid room temperature. And organic chemists have found a way to synthesize it, make it in a plant. And if I had the money, and I had my own company with the right credentials, I could pick up the phone and within 5 days, I don't know, a couple 100,000 pounds delivered to wherever I want, a couple 100,000 pounds delivered. Now, in the last 5-10 years, how many of you are familiar with the trend in children's candy for the super sour stuff? I don't like it. You know, they have the stuff, the more sour it is, the more kids like it. I'm not that kind, I don't get into that, but obviously a lot do because they're selling a lot of it. How do they make it super sour? They just put in more citric acid. I was doing some cooking about 6 or 7 months ago, and I had some recipes and they use citric acid. So there's a favorite place of mine, and I do not get kickbacks from them, I wish I could, but called the Spice House. And I got some citric acid from them, and I wondered, how, this is white solid, 100% pure, 99.95. How sour is this? I went like this, whoa, that is sour. It was really sour. So citric acid is responsible for the taste of the sour in carboxylic acids or products or certain fruits that are sour. You should know that carboxylic acids are responsible, now it switches on, for the sour taste, the smaller molecular weight ones, for the sour taste in various things. Like, I think I don't know, hopefully none of you have done shots of vinegar, but if you've ever tasted vinegar, you know it's sour. And some of the recipes in various ethnic cooking, like sweet and sour, this or that, whatever ethnic cooking you're doing, some of them use acetic acid, some of them use citric, some of them use other carboxylic acids. And turns out some of the carboxylic acids, and especially the smaller ones, really stink. Worst one is butanoic acid. It smells like something like someone just upchucked. How do I know that? Because in the lab I was managing, somebody broke a bottle on the floor, and we cleaned it up, and the clothes I was wearing, like I didn't have food clothes on, that got thrown in the dumpster at the end of the day because it stunk. And they're very polar, they have a sour taste. Because you have a carboxylic acid in the hydroxyl group, just like in alcohols and water, this can hydrogen bond to other things, and that makes it, most of the carboxylic acids have very high boiling points, or they're solids at room temperature, and the lower ones are soluble in water, as you can tell with vinegar. Do you see two separate layers in a bottle of vinegar? No, it's homogeneous, and that's because when R is methyl, because of the hydrogen bonding of the hydroxyl group, it will be soluble. If you had a ketone or aldehyde, same molecular weight, it wouldn't be soluble because those don't hydrogen bond. Like time flies when you're having fun with carboxylic acids. All right, switches on. Carboxylic acids are called acids because they are. They dissociate in water. First of all, what is an acid? I have on the top slide, an acid is, on the top of the slide, an acid is a proton donor, H+. Here's a general acid with a base. You have a proton transfer, and therefore you get the conjugate base and conjugate acid. This is classic acid-base reaction. Therefore, if this happens in a carboxylic acid, and you know water can be amphoteric, in other words, accept or donate protons. Carboxylic acid, the hydrogen on the oxygen of the hydroxyl group, is the acidic proton, H+, from a carboxylic acid. That's why it's called an acid. And you have this acid-base equilibrium where you get this anion. And that's, we'll learn later on, is called a carboxylate anion. So acids are called, carboxylic acids are called acids because they are. Are they as strong as sulfuric or nitric acid? No, but are some of them quite hazardous? Well, at 100%, yes. We'll learn they're weak and strong acids. Vinegar is a weak acid, but even a weak acid like vinegar, if you had more than 4% and you drank it or had it in food, you'd be in the hospital. Now you don't have to worry about that because it's a small amount. Turn your switch off. Why is a carboxylic acid an acid? Why not an alcohol? That's an equilibrium. The little arrow means it doesn't really go to the right. When I take an alcohol, if I remove the proton, this is an acid, I form the alkoxide, which is a very, very strong base because this is a weak acid. Therefore, it doesn't go that way. This does because this is called a carboxylate anion, and I can draw two resonance forms. And that makes this more stable. When you go to something more stable, it's more likely to happen. And that's why carboxylic acids are acids. And with that, I'm going to let you out a whole 55 seconds early. Those of you have lab, please be on time. And make sure you have your safety glasses, goggles, long sleeve top on, I have mine. And those of you who don't, I'll see you on Monday. And don't forget, Monday I'll be going through the problem set ketones and aldehydes. I highly, strongly recommend